Okay, we're recording. This is making no sound. All right, now can you hear me? Yes? Okay, cool. All right, good morning. How's everyone doing? Good? Good? I see we've lost people, but that makes the room more comfortable, so. Yeah, all right, whatever. We'll do, yeah, that probably was really loud. I'm really sorry. I just yelled straight into the microphone. Okay. One thing to point out, the syllabus had the wrong Thanksgiving week on it. So this has been fixed. So if you go to our Canvas page, and go to our updated syllabus, and if you get motion sick, look away. Yeah, so this is our new breakdown. So it's important to note that this did impact one quiz and one homework, I think. Let's see. Yeah, so homework, or quiz 7 stayed the same. Homework 8 is the same. It just changed. Quiz 8 and homework 9 were impacted. And the idea is that it's just not going to be over your Thanksgiving break is the idea. So it'll just be before the break and then, yeah. So we'll just slide that on top. That looks terrible, but you get the idea. The syllabus has been updated. All right. Other than that, does anyone have any questions before we get started? Yes. Yeah, I post my lecture slides. Yeah, so where you can find them is if you go to modules, and then it helps if you just collapse everything else. Click here for the full list of annotated lecture notes. Then there are the slides from last class. Yep. Any other questions? Cool. All right. So the last things to finish up, just looking at important syllabus information. How to do well in the course. Read the tips that I have. I have a full list of tips that are my they work for the majority of students. So normally when students come up to me and they're like, for some reason things just aren't working, those are the suggestions that I make, and it works for most students. If you ever find that those don't work for you, talk to me, and we will find something that will work for you so you can still learn the material. Big thing, make sure you actually do all of the assignments. That seems obvious, but students get frustrated when their score drops greatly, and it's, well, you didn't turn in a quiz, or you didn't turn in a homework. That will drop your grade. Or you didn't show up for an exam and then didn't talk to me about it. Talk to me. Let me know what's going on. I will give you I didn't mean to cross that out. I meant to underline that. I will give you judgment-free help. The point of me and all of your TAs is to help you understand the material. So you should be asking questions. If you are asking questions, that means you're thinking about the course. That means you're thinking about the course material. So there really is no dumb question, because if you're asking a question, that means you're thinking about the class, and that means you're doing your job. So you should be coming up with questions. There should be questions. We want you to ask questions. That's good. That means that you are actually engaged with the course material. That is a good thing. Do active studying. So active studying means don't have the answer key available while you're doing your practice problems. And don't just, I'm not sure, let me check the answer key. Because that's the other thing. Students will be like, yeah, I don't have the answer key out at the same time, but then they don't actually sit with a problem and try to work through it. You want to try to work through the problem, force yourself to think, sit in that discomfort, because that is learning. that process of how can I actually figure this out, that is learning. So you want to kind of sit there and be like, I'm not sure. Okay, let me think about what I do know. Let me go through everything that I do know and see what I can then apply. So it's only once you get to the point where you're like, yeah, I really don't know what to do else here. Like I'm stuck. Then go to the answer key. So that's active studying. Doing as many problems as you can without the answer key present. Make sure you manage your time. It is so easy to fall behind and so hard to get caught back up. And it's something that every semester, it inevitably happens. So you want to make sure that you get like a weekly schedule, like write it down for, Sunday through Saturday, and actually have broken down by hours when you're going to do everything that you do in your lives. Make sure that there are times for organic chemistry on there so that you can get the grade that you want. Also, make sure that you take care of yourselves. So when you schedule out that time, include times like eat breakfast, eat lunch, eat dinner, have a snack, shower, sleep. All of these things are really, really fundamental. You need your brain to do the class. If you don't take care of your body, you don't take care of your brain, you're not going to perform well. So you really do need to actually take care of yourself first, and then you can actually learn the material. So it seems, silly, but inevitably, as we get close to the first exam, and don't get me wrong, I was the student that never followed that advice. That's why I'm speaking from experience of do as I say, not as I did, because as I did was miserable. I did all the all-nighters, and it was awful, and I didn't perform as well as I could have. Don't get me wrong, I'm still happy with my grades. I still ended up here, but, sleep. Sleep is really fundamental. Do it. All right, and ask questions. All right, speaking about health, if you are sick, please don't come and share it with the class. Please keep it to yourself. So if you really are contagious or you're throwing up, I had a student who wanted to come in and they were like, I'm projectile vomiting. Is it okay if I still come to lecture? No. No, it is not. Please stay home, take care of yourself. Organic chemistry can wait. Get well, and then we'll figure out how to get caught back up. So email me as soon as possible so that I can help you. We can adjust any sort of schedule. We can get you makeup assignments. You can get an extension on a quiz or the homework, whatever. Your well-being is very important to me. I can only help you if you let me know that you need help though. So tell me and I will do everything I can to help you out with the class. Cool. Some extra resources. So on Canvas, we have various resources. I recommend everyone talks to SLDS. It's just a really great resource that I didn't even know about when I was in undergrad, that universities have to have this disability service center. And even though the word disability kind of feels like, well, maybe I don't have a disability, if you get really anxious during tests, that counts. So you could potentially get extra time on an exam, or if you get really distracted easily, you might get a private class or private room to take the exam. And also, it's totally anonymous. So you can go talk to them, find out your options, and then decide, I don't want to do it. And that's cool. You just don't do it. And that's fine. You get to pick which ones you get to use. So I always recommend people talk to them, find out your options, especially early on, because it's not retroactive. It's only proactive. So that means if you only figure it out about halfway through the semester, half the semester doesn't get to have the benefits of the extra time accommodations or whatever else you are given. So I always recommend people talk to SLDS just to find out what your options are. Then there's also various diversity-related resources, extra mental health resources. Just if you ever need help, if you ever feel like you are not safe, please let me know. So with that, I do want to acknowledge the fact that our classroom has an extra safety feature. So our classroom is, one, a shelter location. So if we have a tornado or there's any sort of inclement weather, this is actually where people will gather. So we would actually have other people in the building come join us. because this is a shelter location. So it is a safe room. There are no external windows. That's what helps makes us safe. Also, in the event of an active threat, we have these blue emergency pull tabs. So the red ones, do we not have a fire emergency? All right, well, the ones that are red, that we apparently don't have in this room, indicate fire. The ones that actually say emergency, these are for the active threats. So we have 4 in our classroom. So there are 2 in the front, 2 in the back. And when you pull that, it locks down our room. So it locks us in. I mean, we can still leave if we have to. So if like a fire were to start in here, which hopefully no one would be like smoking or anything, but if we had to evacuate, we could, but it keeps anyone from coming in. And it'll indicate it switched over to red. When it switches over to red, that is telling us that it has called the police for us. So we wouldn't have to call the police. It will call the police for us, and it will notify the police that our room needs attention and needs help. So that is an added safety feature of our classroom to try to make sure that you are all safe and we all stay safe. Because if you don't feel safe, you can't learn. If you can't learn, I can't teach you. That means I can't do my job, you can't do your jobs as students. We got to make sure that this is a safe learning environment. So if there's ever anything that makes you feel uncomfortable or unsafe, please let me know and we will fix it. It is very important to me that you feel safe. All right, so some reminders of, all right, where do I get help? There's going to be the TA help room, which is Evans 1042. There's going to be a list of tutors that our course coordinator, that's Rebecca Patton, will manage. Don't forget that my office hours, starting on Monday, are going to be in person in McPherson 1041, and it'll be right after this lecture. So basically, we'll just, whoever wants to join or is able to join, we'll just walk over to McPherson and we'll just answer any questions, right? Does anyone have any questions about anything for the course? Cool. All right, let's start chemistry then. All right, so I have adjusted this because I didn't correct it before posting it and making it available to you. So we are Monday, Wednesday, Friday, so make sure you show up today on Fridays. And we are in the fall of 2024. We also have the added benefit, so I post this mostly to let my summer students know that the course is accelerated. We are not, we're in a standard semester. So we're only gonna do about 15 to 16 pages per lecture, which is a pretty normal pace. For chapter 1, we're going to be getting into just some general introduction. We'll be doing a Gen Chem review. We're gonna spend quite a bit of time talking about resonance and how to start to look at reactions. So our big thing is just, what do you need to know from general chemistry to be successful in organic? Make sure you remember that. And then also start to learn about how to kind of apply it in organic chemistry. So organic chemistry is the study of compounds that contain carbon and hydrogen. That is what makes you an organic compound. It is what is necessary for life, for living organisms to exist. So you, me, every plant, everything that is alive or was alive contains molecules that have both carbon and hydrogen. Wohler in 1828 proved that you didn't need to actually harvest organic molecules from living organisms. You could just make an organic molecule from a chemical reaction. So Wohler took lead cyanate, which is not organic. Although it has carbon, it does not have hydrogen, so it's inorganic. Water and ammonia, so all of these are inorganic, meaning not organic, and made urea. Does anyone know what urea is a common component of? Yeah, urine, that's pee. He made pee in a bottle. I know it's more complicated, it's easy to harvest urine, but this was pure. This was a pure form of urea. So this was like groundbreaking. This was a huge thing. And this is organic because it contains carbon and hydrogen in the same compound. And then there was also lead hydroxide, which is just a byproduct. But we don't care about that because we care about carbon because we're organic chemistry. So carbon is really important because it's going to make strong bonds to other atoms. And carbon-carbon bonds themselves are also really strong and inert, which makes sense because they're nonpolar bonds, right? They're nonpolar covalent bonds because they're the same atom, so they have the same difference in electronegativity. That's going to be a really strong bond. Neutral carbon is going to make 4 bonds. This is extremely important that you remember this. It is so important that I'm going to do a call and response. I'm going to say neutral carbon makes, and you are going to say 4 bonds. All right, you ready? Neutral carbon makes. Neutral carbon makes. Neutral carbon makes. Neutral carbon makes. All right, we're good. Cool. So I always do it 4 times for 2 reasons. One, one, actually just kind of parallelism. So 4 bonds 4 times makes sense. Also, doing things in 4s, there have been some studies to indicate that level of repetition makes it a more significant neural pathway, meaning that you're more likely to remember it. Remember, neutral carbon makes 4 bonds. Very important. That 4 bonds, that's a lot of bonds. That's a lot of opportunities to connect to other atoms, have other types of bonds. We can do single, double, triple. We get lots of combinations of these bonds and arrangements of the atoms. That is going to lead to a lot of synthetic diversity. So we can make all of the molecules that make you a living organism based on the fact that carbon has all of this variety to it. So where is organic chemistry found? Where is it used? Literally, with the true meaning of the word literally, everywhere that life exists or existed. So my favorite, really simple reference that I think is like super tangible is using methylamine. So methylamine is the kind of common compound that leads to the fishy odor. So if you've ever smelled fish and been like, ew, that smells fishy, you're smelling methylamine. That's what you're detecting, is that compound. When you cook fish, you typically add lemon juice to it. Like you'll cut up lemon or add some lemon juice. You're adding acid. By adding that acidic proton, you are going to make methylammonium salt. The thing to know about methylammonium salt is this is now ionic. Remember, ionic compounds tend to have really high melting points and boiling points, meaning it's a solid, which means you aren't able to smell it. It doesn't readily become a gas. You smell gases. So by adding lemon juice, what you're doing is you're making the really unpleasant molecule turn into a solid so you can't detect it. So you can't smell it, you can't taste it, and that's why it tastes better. So I just think that's so cool that it's like all we did was add that H+, and now all of a sudden the molecule is more pleasant to interact with. So let's review Gen Chem. Let's get into what parts of Gen Chem do we still need to remember. Because it's not all of it, but it is a good amount of it, especially Gen Chem 1. When we look at our atoms, we have our nucleus, which is made up of our protons and neutrons. Those protons determine the identity of the element. You cannot change the number of protons without changing the element. Neutrons we will be able to change. That's going to make our isotopes. And then outside of our nucleus, we have that electron cloud. In our electron cloud, we have electrons. Those electrons are going to determine our charge. our bonds, and our reactivity. We're going to spend all semester talking about electrons. Where are they? Where are they not? How can they start here, go there? Those are going to be our chemical reactions, is where do the electrons begin? Where do they go? So we're going to really just emphasize electrons. They're going to be a really big part because they control all of our reactivity. That electron cloud, we want to remember, it is going to be arranged in shells. These are essentially just energy levels. Also, I am a horrendous speller, so I'm going to use a lot of abbreviations. If you ever don't know what my abbreviation means, ask. So capital E is energy. LVL is levels. Bless you. Those energy levels are going to be related to our periods, our rows on the periodic table. What holds our atoms together is the simple fact that opposite charges attract, same charges repel. So our nucleus is positively charged, having the protons and neutrons, and then our electrons are negatively charged. So the opposite charges, positive and negative, are attracted to each other. That's what holds the atom together. All atoms are neutral by definition. That means that the number of protons equals the number of electrons. When we look at our atomic symbols, we need to be really careful about capitalization. So every element will have one and only one capital letter. That's what distinguishes it from a compound. So if I were to write this first one, I have a big C, little o. What is that? Cobalt. Very good. Whereas this next one, I have big C, big O. Carbon monoxide. Beautiful. Look very similar to very different things. So you need to be really deliberate and intentional with your capitalization and with how you're writing. This is particularly becomes an issue on exams where students are just usually are used to writing in all capital letters, and then they're writing things that aren't, like they're mixing up elements, compounds, all sorts of abbreviations. You must be intentional with capital and lowercase letters. Our periodic table is usually going to show our compounds or our elements where we have the element abbreviation in the middle. Our atomic number is above, and our atomic mass is usually below. It doesn't have to be that. You would usually look at some sort of key to tell you. You will always know which one is the atomic number versus the mass because your atomic number is always smaller, right? Because the mass is going to be made up of protons and neutrons. Your atomic number is the number of protons. So your mass must be bigger than your atomic number. Our nuclear symbol, which is how we're going to abbreviate our elements, is going to have that element symbol in the middle. In the upper left-hand corner, we get that atomic mass. So that is that protons plus neutrons. In the lower left-hand corner, that's where we put our atomic number, the number of protons. In the upper right-hand corner, we put our charge, which gets abbreviated Q. And it's important to note that if nothing is written, that means that it is neutral. We assume a charge of 0 if nothing is written. So what that tells you is if it is charged, then it must be written. If you have a positive charge, you must write it. If there is a negative charge, you must write it. Otherwise, we assume it is neutral. In the lower right-hand corner is where we write the number of those atoms. So that is just our normal subscript. If nothing is written, we assume a 1. You assume you have something. If you're writing it, you assume there's something there. If your atomic mass and your atomic number are not written, what do we assume? Yeah, you assume that you got to look at a periodic table. Yeah, right? That's where we get all the information, is on that periodic table. It's where we find it all referenced out. Yeah, we look it up. We can look it up on a reference. So you'll always be given a periodic table. On every quiz, every exam, you will be provided one. You don't have to have your own. You actually won't be allowed to have your own. Well, the quiz you can, because it's open note, but on the exams, I will give you a periodic table. All right. So we had said the isotope, that is where we have an atom, but we have changed the number of the number of neutrons. So we have added or subtracted our neutrons. It's important to note that it's going to have the same chemical properties. It'll just have a different atomic mass. So it'll behave very similarly. So common isotopes that we deal with are the isotopes of hydrogen. So there's also carbon. Carbon-13 is very relevant. And in case you don't remember, that's how we read it. So like this is carbon-13. You say what the atomic mass is after it when you're reading it. But the ones that we're really going to worry about, we will worry about carbon-13, we will worry about oxygen-18, but the main one that we're going to focus on is going to be deuterium. So let's look at hydrogen first. How many protons does hydrogen have? 1. How do you know? That's the atomic number. Beautiful. How many neutrons does hydrogen have? None. How do you know? It's the mass minus the atomic number. So it's 1 minus 1 is 0. How many electrons does hydrogen have? 1. How do you know? Because it's neutral. And because it's neutral, your number of protons equals your number of electrons. You know it's neutral because nothing is written in the upper right-hand corner. So that is your indicator to assume the number of protons equals the number of electrons. All right, so let's do deuterium. Deuterium usually is abbreviated as a D. This usually trips students up because they think that it's an element, but it's not on the periodic table. It is hydrogen, but it's just an isotope. So how many protons does deuterium have? 1, because it's still hydrogen. And remember, you can't change the number of protons without changing the element. We didn't change the element, it's still hydrogen. How many neutrons does it have? 1, that's what we changed. We added a neutron. That's how we increased our mass. How many electrons does deuterium have? 1, how do you know? It is still neutral, right? The charge is still neutral, so the protons and the electrons equal each other, because that's where we get our charges. Tritium is another isotope of hydrogen. How many protons does tritium have? 1, how do you know? Because it's still hydrogen. How many neutrons does it have? 2, how do you know? 3 minus 1. How many electrons does it have? 1, how do you know? Because it's neutral and the number of protons equals your number of electrons. Beautiful. For our ions are going to be where we are adding or removing electrons. If you are adding electrons, what does that make? An anion, good. If you subtract electrons, what does that make? Cation. Beautiful. So hydrogen, neutral hydrogen, we had already said that those were the number of protons, neutrons, and electrons. For this hydrogen cation, how many protons does it have? 1, because it's still hydrogen. How many neutrons does it have? 0, because its atomic mass is still 1. How many electrons does it have? 0, good. This is why we are typically going to call our hydrogen ion a proton. So when I wrote H+, and I said that we are adding a proton, it's because that's what it literally is. It is just a naked proton. There are no neutrons, there are no electrons, it is just a proton. Our periodic table trends, the important ones to remember is that our electronegativity is going to increase as you get closer to fluorine. That is going to be our most electronegative atom. So as you go up and to the right, that increases your electronegativity. As you go down and to the left, that increases your size. So francium is the largest atom. Fluorine is the most electronegative. So as you get closer to each of those, you get those approximate sizes. With our periodic table, groups 1 and 2, where groups are the columns, this is called your S block. Groups 13 to 18. This is your P block. And then everything in the middle, that is your D block. And your F block, I omitted. It's the ones that are like down here. That's F, your lanthanides and actinides. So we use those to indicate our electron configuration to know where our valence electrons are located in those orbitals. All right, so we remember what electrons are. Let's talk about what we can do with them. We make bonds. Bonds are a pair meaning 2, electrons. We're going to represent these bonds with lines. We form these bonds because this is a stabilizing interaction. This is going to make our molecules more stable, makes our elements more stable, and is going to lower our energy. So what determines the number of bonds to each atom? It is valency. Valency is the number of bonds an atom typically has in order to be neutral and have a full valence shell. Because that's really what we're trying to do, is we're trying to fill our valence shell. We want to be like our noble gases. Want that noble gas configuration, full valence shell. It relates to the octet rule. So carbon wants 4 bonds, which we already said, right? Neutral carbon makes 4 bonds. So it is tetravalent because when it is neutral, it wants to make 4 bonds. Nitrogen is going to be trivalent, tri meaning 3, So nitrogen typically will exist with 3 bonds and 1 lone pair of electrons. Oxygen is divalent. It wants to make 2 bonds and have 2 lone pairs of electrons. Hydrogen and our halogens are monovalent. They want 1 bond. Our halogens are that group 17, so that's our fluorine, chlorine, bromine, iodine. It is going to be really useful if you just memorize that. It's going to make it way faster to draw structures if you just know their valency. You know how many bonds they want to make when they're neutral and how many lone pairs of electrons they have. It's going to make life so much easier to just memorize that. Our hypovalent, hypo meaning less, are those atoms that are neutral and stable with less than 8 valence electrons. So the ones that are really significant are things like boron and aluminum. Those are the big ones that we usually will show, because that's how they exist, of boron and aluminum with 3 bonds and no lone pairs. And they will just be neutral, and they will be stable that way. They don't have a full octet, so they are hypovalent. Hypervalent, hyper meaning more, are going to be atoms that are neutral and stable with more than 8 valence electrons. My PhD research was actually on hypervalent iodine. So I worked with iodine that was forming 3 bonds, which made it unstable because iodine wants 1 bond. I forced it to have 3. It made it a really good oxidant. The most important thing that you can memorize right now is that periods 1 and 2, so rows 1 and 2, cannot exceed their valency. They cannot make more than 4 bonds. It is not possible. It is not possible because they do not have a place to put the electron. They don't have an orbital to put it in, right? Because when you are in period 2, row 2, you only have S and P orbitals. You don't have a D orbital yet. So you are unable to make more than 4 bonds. So carbon, nitrogen, and oxygen, in particular, make sure that they never have more than 4 bonds. More than 4 bonds, it is wrong. There is usually, in inorganic chemists, they usually like to go, actually, we have been able to find carbon in the middle of, I think it's manganese or iron, as a complex at like the bottom of the ocean, where they made carbon have 5 bonds. And this was like a big deal because it violated everything that every organic lecturer has ever said. And they were really stoked. And what I'm going to tell you is, that's really dope, actually. But we don't live on the bottom of the ocean. We live here on the surface. So here, in this classroom where we live, we will never draw more than 4 bonds to carbon. We're not going to do it. Not to carbon, not to nitrogen, not to oxygen. We will not exceed their valency. Our octet rule is kind of a garbage rule because there are more exceptions than there are obeyers of the rule. But it's useful, so that's why we still teach it. So the octet rule is saying that there are those 8 valence electrons that we try to get in our valence shell. That is that noble gas configuration. It is most stable. The only elements that really obey the octet rule are carbon, nitrogen, and oxygen. That's pretty much it. because they only have s and p orbitals. So they're really going to be hard and fast followers, which is why we're still teaching the octet rule, because there's a lot of molecules made up of carbon, nitrogen, and oxygen. It's important to note that there are a lot of exceptions, though, to the octet rule. Essentially, everything outside of period 2, everything outside of row 2 are going to be exceptions. And actually, even in row 2, we also have exceptions. So there's the duet rule. Duet rule meaning only 2 electrons in the valence shell. What are the 2 elements that have that? Hydrogen and helium. Yeah. Why do they follow the duet rule? They only have an s orbital, right? Remember, the s orbital can only hold 2 electrons. So because they only have that s orbital, they stop at 2. They are then full at 2. So what that means is hydrogen and helium will never make more than 1 bond. They will only make 1 bond. Our radicals are unpaired electrons. So they are usually written just as like Cl dot is how we will represent the radical, because that's kind of the relevant portion. It actually is chlorine with only 7 valence electrons. On its own, it is neutral, just as that. Like when we calculate our formal charge, that is neutral. But the stable version is chloride. That chloride is where you have the full valence shell. It gains 1 electron because it wants to fill its valence shell, fill its p orbital, and it takes on a negative charge. So radicals are an exception to the octet rule because you can be neutral and not have a full octet. They're not usually stable, but there are varying levels of stability with them. Carbenes are going to be a neutral carbon that only has 2 bonds and 1 lone pair of electrons. It is not hypovalent because it is not stable, but it does have 6 valence electrons. So it is an exception to our octet rule because it is existing with 6 instead of 8. Our hyper and hypovalency are also exceptions. And the things to note are boron, that boron in the aluminum, group 13, it is going to have an empty p orbital. It has a place to accept electrons so that it can actually fill its octet. That means it's going to be what we're going to call a really good Lewis acid because it has that extra location to take electrons. It has a place to put them, so it can, and that's going to be the definition of a Lewis acid, is something that can accept electrons. So if you ever see boron, aluminum, and pretty much all of our transition metals, not all of them, but pretty much all of the ones that we're going to work with, they're going to be Lewis acids. All right, so how do we get an octet? How do we be neutral, stable, and have that full valence shell? We form bonds. That is how we do it. So you can form an ionic bond where you have the transfer of electrons from a metal to a non-metal. So remember that your ions are metal to non-metal. You have sodium chloride, so that separates into Na+, that is your cation, Cl- is your anion. So here are Jim and Frida. Jim, unfortunately, just passed away, so that's really sad, and I didn't delete him because I love him. But anyway, so there's Jim and Frida. and they are my cations. I think very positively of them. I love them very much. So if you like cats, you can remember that you think positively of cats, and so that the cations are positive. If you don't like cats, remember I like cats. And Dr. Walters thinks very positively of cats, so therefore the cations are positive. Do whatever you gotta do. Remember, cations are positive. With our covalent bonds, that is where we are sharing our electrons between two nonmetals. So that's the big difference. Ionic, you have to have a metal and a nonmetal. Our covalent is two nonmetals. We have two types of covalent bonds. We have our polar and our nonpolar. We determine that based on the difference in electronegativity. As you increase the difference in electronegativity, that increases the polarizability of the bond. So as you get a greater difference in your electronegativity, you become more polar, is all that's saying. I like using this diagram, whatever it's called, to kind of illustrate that difference between our nonpolar, polar, and ionic bonds. So if you are looking at this x-axis, it is the difference in electronegativity. That triangle is the capital Greek letter delta, and that means difference. It also can mean heat. You have to use context clues to know which one. Here, we're talking about difference. So it is, you subtract their electronegativities. As you go from left to right, you are increasing your polarizability, increasing that polarness of the bond. That was bad grammar, but whatever. If you are between 0 and 0.4, including 0.4, then you are a nonpolar bond. Nonpolar covalent means that you are equal sharing your electrons, pretty much equal sharing. If you're 0, that's a true nonpolar bond. That is pure. You are really equally sharing. Our polar bonds are anything greater than 0.4 up to about 2.1. That number, that upper limit, is highly variable. It depends on what is your system for calculating the numbers. So we typically use the Pauling system to determine our electronegativities. There are 4 different systems. None of that matters. All that matters is that the number up here, you don't need to memorize that. That number doesn't matter because we're going to use a very easy, simple thing to determine this limit. And that is, do I have a metal? If I have a metal, I am ionic. If I don't have a metal, then I do math. So I'm not going to care about that top number. That top number actually is meaningless. Don't memorize it. Don't pay attention to it. 0.4 is important. Know that number. That number is important. But 2.1, whether it's a 1.7, 2, 2.1, none of that matters. You are going to be a polar bond, unequal sharing, if you are greater than 0.4 and you are two nonmetals. You'll be ionic if you have a metal, regardless of the difference in your electronegativities. We will typically focus on our polar bonds. That's where we're going to get a lot of our reactivity. A lot of chemical reactions are going to occur where we have that difference in location of electrons. Where are electrons typically hanging out? The greater concentration of electron density in one place, lower in another, that is our chemical reaction. So we're going to focus on polar bonds. So identifying the polarity of a bond is going to be extremely important. That's something that you want to make sure that you're really good at from Gen Chem. Also, just a really quick thing, with carbon, the carbon-hydrogen bond is a nonpolar. The difference in electronegativity is 0.4. So that's actually how I memorized the 0.4 number. Was I knew carbon-hydrogen was nonpolar, and the difference in their electronegativity is 0.4, so I know that's the limit. And then carbon-carbon is going to have a difference of electronegativity of 0. so nonpolar. Carbon-2, anything else? We're going to call it polar. So you don't actually even really need to do math. If you ever do need to calculate electronegativities, you'll be given the electronegativities. Do not memorize the numbers. That is not worth your brain space. I mean, you can if you really want to, but I'm never going to ask you the question without giving you the numbers and then having you do the simple math. But if I'm just trying to get you to identify, is the bond polar or nonpolar? Recognize carbon-hydrogen, nonpolar. Carbon-carbon, nonpolar. Carbon, anything else, that's going to be a polar bond, so we can really quickly recognize it. Dipole arrows are what we're going to use to show the difference in electronegativity of a polar covalent bond. There is one exception. There is a homework question that was a weird noise. There is a homework question that has a carbon-hydrogen bond that is recognizing that there's a difference in 0.4. On that one homework question, the way that it is phrased is it says use a dipole arrow unless it is a true nonpolar bond, meaning they have exactly the same electronegativities. Meaning when you get to that carbon-hydrogen bond, put in the dipole arrow. And that one homework question will be the only time. There isn't a very good variation of that question, so yeah, that's why I leave it in, and then I just tell you that's how you get the question right, is that one homework question, for that one time, put a dipole arrow on that CH bond. Our dipole arrow is always going to point towards the more electronegative atom. That is the delta negative. The delta, this is the Greek lowercase letter delta. It is like the S won't quit or a circle with a little top hat. So it's like S, but it keeps coming around. That is the lowercase delta. That means partial charge. So our dipole arrow points towards the more electronegative atom, the partial negative. So the tail is at the less electronegative. That is the partial positive. And a way to easily remember this is the tail kind of looks like it has a little plus sign on it. So that's where the positive is, and you always point towards the negative. Cool. Does anyone have any questions about all of that, any of that? Yes? So all halogens will exist in their neutral state as radicals because they're in group 17 and they're one electron away from filling their octet. So their halogens are going to be common sources of radicals. Cool. Are there any other questions? We're actually not out of time quite yet. Yeah. Hang on, I can't hear. What's up? All right, I'll fix the calendar again. I'll find that. I don't know how, okay. I don't know how many times I can look at that calendar. I will make sure it's absolutely right. Thank you. All right, any other questions? All right, have a wonderful day.